Hi, today I will talk to you about how you can respond to new information in a mining complex using fast mechanisms that are inspired from machine learning methods. And I'll start with an introduction where I will discuss mining complexes and global optimization of mining complexes. And then I'll talk about how you can adaptively respond to new data using these machine learning methods in general. And this has been a focus of my work for the last couple of years. But what is new in this presentation, what is exciting about this presentation is a detailed case study for the Escondida mining complex, where we have built an hour-by-hour model of the material flow, and it's a stochastic model. And because this is more complex than anything else we had to deal with before, we also had to improve the method we use for the machine learning method we use for adaptive decision making. In this case, we use modern methods based on neural networks. And finally, we show how the results of using the neural network policy compared to using a cutoff grade policy. And we end with conclusions and future work. Okay, so as everybody knows, in Cosmo, we're interested in global mining complex optimization under uncertainty. And I have a diagram of mining complex here where I have a couple of pits, a couple of leach pads, 3 crushers, 3 plants, and all these arrows indicate possible material flows in the mining complex. So the idea is to optimize those material flows simultaneously with extraction and let's say operational options at the plants, etc. Basically anything that can be optimized simultaneously, and to do this under uncertainty. So more and more in the last, let's say, decade or so, a lot of sensing capabilities has started to be incorporated into the mining complex, and this produces a lot of data that can be obtained about the various components of the mining complex. So for example, this could tell you where your material is and what its quality is, the material that's being sent, and it could tell you what are the properties of the material that has been blasted, and where your equipment is, how well it's performing, etc. And the idea of this presentation is to incorporate this type of data into decision making through these adaptive decisions. So right now, what's happening in a lot of mining operations is that this data is being interpreted by a person who then makes a decision about what the best course of action is. But since there is more and more data available, this is making good decisions is starting to be more and more difficult for human operators. So we want to improve their productivity through better automated computer-assisted decision making. And one way to do this would be to simply re-optimize. Let's say you have an optimizer that gives you an original plan, but then anytime you get new data, you could re-optimize and get a new course of action, or tell or try to help the person decide what the best course of action would be. However, the problem with this is that once again, with a lot of data, it can be slow to re-optimize, and this means sometimes time-critical decisions cannot be taken fast enough. But it is also difficult to integrate short-term or operational planning with long-term planning if your operational planning involves computationally expensive re-optimizations. So the alternative we propose in this talk is to replace the re-optimization with the methods inspired from machine learning that are in some sense pre-optimized to know how to respond to new information. And in this case, I'm showing a neural network because this is what we're going to use for the particular case study. And to show you how this works, let's take an example where you are trying to send a block that you've extracted to one of the possible destinations. So the data in this case could consist of information about the block, such as the grade, the tonnage, other elements in the block, the status of your equipment, wait times to the different components of the mining complex, and the performance of the plant, etc. So all of this can be put into a numerical vector, and this is then fed into this neural network in this case. And if we want to decide, for example, whether we allocate the block to either the plant or the waste, the neural network could produce as the outputs for the two output nodes could produce two different probabilities. One indicated the probability of the plant decision being optimal, and the other one being indicating the probability of the waste decision being optimal. And depending on how close these probabilities are to 0 or 1, the operator or worker can then make an informed decision about what the best course of action would be. So what happens inside this neural network is we have these connections here, these arrows, and they represent weights that get multiplied. So for the first layer, for the leftmost layer, these weights get multiplied by the input, the values in the input nodes, which, as I said before, are given by the numerical representation of your data. And so you get all these linear combinations of the input nodes, and you get one of them for each of the hidden nodes. And at the hidden nodes, then the value that you get from this linear combination is then being passed through a nonlinear function, fairly simple nonlinear function usually, like a sigmoid. And then the process gets repeated where the values that you get at the hidden nodes become part of this linear combination that gets sent to the output nodes, and then there's another nonlinear function that in this case ensures that the output values are between 0 and 1 and sum to 1 because they are meant to be probabilities. So you can see how this can allow you to represent very complex nonlinear functions, and with this we can represent the complex types of adaptive decisions that you might have to take in a mining complex. Now, of course, the problem is how do you figure out what those weights should be? And the general framework for doing this for our problem is to start with a stochastic model of how a mining complex works. And this model can be used to simulate, to generate basically artificial data about what happens time step by time step in the mining complex. And then this data, as explained on the previous slide, when it's fed to the neural network, can be used to produce a decision. Then the decision combined with the stochastic model can be used to evaluate the improvement in the objective function we're interested in. And then this is the crucial step where the weights get updated. The subjective function is taken and it's being used by gradient descent methods, in the case of neural networks, to update the weights to basically move them in the direction in which they would improve the objective function. And there has been a lot of progress in recent years about a more clever gradient descent methods, because this is a fairly complex function to optimize, but these methods have been getting better in last years at avoiding, let's say, local optima and converging faster and so on. So for the case study, we have exploited these new and improved methods for training neural networks. For the case study, we considered the Escondida mining complex, which some of the other presentations have also addressed. And just to have a brief, just to recap briefly, there are a couple of different, there are two different pits, and the material from the pits can be sent to 3 different plants, or to the leach bed, or to the bioleach. And there are 4 different crushers for the plants, and and one for the acid leach bed. And there are different paths according to which the material can flow between the pits and the crushers and the plants, as can be seen in this figure. And for the case study, we assume that there are 5 shovels at each of the pits. So we built a stochastic model of the operation of the mining complex. And this model will operate at an hourly timescale, and it will be used to make destination decisions for every block that is extracted. The main components are the shovels, the crushers, the plants, the leach pads, and the durations the material takes to get between them, which are determined by hauling equipment and by conveyor belts. So the model we built, I want to emphasize, is not necessarily uh, it's not based entirely on data. Some of the choices have been made to get a reasonable approximation, to get something that would have the complexity of the Escondida mining complex. But since we didn't have data for every component, I do not claim that it actually completely reflects the way it operates. For example, for the shovel, we assume that the shovel is normally in an operating state, but according to a time to failure, which we assume to be exponentially distributed, it fails, and then when it has failed, it takes a certain amount of time for it to be fixed and to become operational again. And this is given by in our model by a log normal distribution. And these are just choices that we made because from talking to people, it seems like those are reasonable choices for modeling these waiting times. However, they once again do not necessarily reflect this particular mining complex, and better models could probably be produced given let's fine-grained, accurate data. Okay, with this disclaimer, we also assume that the productivity of the shovel, measured in tons per hour, is distributed according to a normal distribution. And for the crusher, we use the fixed throughput for each crusher. However, the amount of material that is being sent to the crusher is not fixed, it's stochastic because it's being determined by the shovels and the cycle times of the trucks. And when material is being sent to the crusher from different shovels, which happens pretty frequently, we assume that an equal fraction of the material sent by each shovel will be processed within each hour. So in the end, we have this heuristic way of modeling the extraction time for each block, which takes the maximum of the tonnage of the block divided by the shovel throughput, of the cycle time of the truck, which we assume to be a truncated normal distribution, and of a fraction of the block crushing time. So if it takes, so this is the crushing time for the block given all the other blocks that have been sent to the same crusher. And this is just to say that if your hauling equipment has to wait for the crusher to basically process all the material, then your extraction time should increase. We also had stochastic components associated to modeling the operation of the plant. For instance, for recoveries, we assume that recovery is a stochastic function of the grade. And in this figure, you can see daily grades and recoveries. And you can we modeled the stochastic function by modeling its grade-dependent mean and standard deviation. So the mean is the green line, and you can see it's an increasing function of the grade. And the standard deviation, you can see that there's more spread for lower grades than for higher grades. So we had a grade-dependent standard deviation also, and the red lines correspond to two standard deviations above and below the mean. And for normal distributions, this would you'd have 95% of the values of the sampled from the distribution between the two standard deviations, and you can see that this works fairly well for this data. We didn't actually use a normal distribution because that is unbounded, but we're bounded below by 0 and above by, we assumed, 95% recovery, so we used the truncated normal distribution instead. And we did something similar for the arsenic and concentrate, because for this mining complex, it's important not to have too much arsenic in your concentrate, and you actually get a penalty in your objective function, or you basically have a cost for sending to the smelter material that has too high of a concentration of arsenic. And the way that the plant processes material is that the conveyor belts, we assume, deposit material on the feed pile for the plant, and then material gets taken from the feed pile and processed at the plant. And whenever the amount of material on the feed pile is too low, then we assume that the processing rate decreases so that the plant does not basically have to stop for too quickly for a lack of material. We also assume that there is a fixed cost that is incurred every hour that's irrespective of the amount processed. Just for spinning the mill, no matter how much material you have, there is a fixed cost. And this means that we don't need a lower bound on the plant tonnage, because if the plant tonnage is low, then you will get an implicit penalty by having to incur all this cost anyway without producing much revenue. So for the rest of the parameters, we used a total of 6 months with a predetermined extraction sequence and 15 geostatistical simulations that were produced by Ashish, and 10 were used for training the parameters of the neural network, and 5 were used for testing the performance of the neural network-based method. And you can see here the ranges for the other parameters for the shovel throughput, the crusher throughput, the plant throughputs, etc. And we only considered copper output, not gold, and we considered penalties, as I was saying before, on the amount of arsenic in concentrate. And we looked at determining destination policies. So for each block, you have several potential destinations. These include the 4 crushers corresponding to the plant, so you decide which of them you would send the block to. They include the acid leach, the bio leach, and the waste dump. And every hour, we assume that each crusher sends the material that's being crushed to the plant with the lowest stockpile for that hour. So this is a part of decision making that is not optimized right now. And the baseline policy that we compare to is a optimized cutoff grade policy. And this works. So first you have you try to determine basically how much your material is sulfide or oxide by looking at this soluble to grade ratio that is denoted here by SR. So this just divides the copper solubles by the copper grade of the material. And if this ratio is below 0.2, then depending on your cutoff grade, you would send the block to either the plant or the bio leach, or if your grade is really low, to the waste dump. If it's between 0.5 and 0.2, then your block can be sent to either the bio leach or the waste, depending on its grade. And if it's above 0.5, then if the amount of soluble is above a certain cutoff, then it gets sent to the acid leach, and otherwise it's being sent to the waste dump. So before showing comparisons to the neural network policy, I just wanted to look at the effect of modeling of the stochastic model that we built. And we see in this graph, we have the profit of using the cutoff grade policy with a deterministic version of our model as the red star at 100%. And including equipment uncertainty, then we have the green star and the green crosses corresponding to P10 and P90. And we can see that, so the deterministic model does not consider the stochastic breakdowns or the stochastic hauling times and cycle times that we considered. So you can see that it's fairly optimistic. It seems to be fairly optimistic with respect to the value you would get, as opposed to what you get when you include the equipment uncertainty. When you include the geological uncertainty, you get a even wider range of possibilities. So this is the blue part corresponds to only including geological uncertainty, so only looking at the variability from the simulations. And the reason why this gives, on average, higher values than the deterministic setting is because the parameters of the cutoff grade policy have been optimized with respect to the to the stochastic model, so with respect to these particular simulations. So it's normal that we get a higher value. And when we combine the geological and the equivalent uncertainty, and we do this by randomly sampling a simulation and then randomly sampling cycle times and plant performance from our model, then we get about the same spread of values as for geological uncertainty, but we get the range is significantly lower when we include equipment uncertainty. Okay, so now going to our comparison, what we'll do is we take the baseline policy, we take the same structure where we look at the what the soluble to grade ratio is, and we allow this to limit our choices in the same way. However, the choices for each range of this ratio are going to be based on the output of the neural network instead of being based on cutoff grades. And so yeah, the weights of the neural networks will, as I showed before, be optimized in order to maximize an objective function that basically just maximizes the cash flows for the period we're looking at. The inputs for the neural network consist of the properties of the material that's at the various components of the mining complex, and these properties can include tonnage, grade, amount of soluble copper, amount of arsenic, and we can look at the different destinations, such as the crushers and what's happening on the conveyor belts, the material on the feed piles, etc. We're also, because we're looking at allocating a block, we are looking, of course, at the properties of the block being allocated, but also at the properties of the material that's going to be extracted at different shovels during the next hour, to sort of know if we have other good material incoming. And here we can see the range of values that we obtain with our stochastic model for the optimized cutoff policy and for the neural network policy. And we can see that there's a significant improvement when we use the neural network policy. And you get about 7% more value on average than when you use the optimized cutoff grade policy. So now if you want to look at into more detail about why this happens, we can look at the tonnages that the tonnage of the material that's being processed at the different plants. And for the optimized cutoff grade policy, you can see that there is quite a bit more variability than for the neural network policy. So the OGP1, Los Colorados, and Laguna Seca are the three plants. And we can see that especially for OGP1 and Laguna Seca, the neural network policy does a much better job at ensuring basically a consistent tonnage at the plants and avoiding these, not avoiding, but justifying these fixed costs that are being incurred for each of the plants anyway. And to see a little bit more about how this is being done, if you look at the grade that's being processed at the plants, you can see, at least at OGP1 and Laguna Seca, that there is more variability in the neural network policy which is not constrained by a cutoff grade. So you can see that sometimes, for instance, around day 40, it can end up processing lower grade, but this ensures that you don't have a big that you still process something at the plant, even though you go below the cutoff grade of the cutoff grade policy. On the other hand, sometimes you end up being more selective about what you processed, and you process higher grade than would be processed by the cutoff grade policy, and this allows the policy to avoid wait times at the crusher, for example, or on the conveyor belts, and because of this, you basically have a smoother material flow, and our policy, the neural network policy, achieves an increase of about 5% in shovel productivity as a result. And to look more into the type of decisions that are being made, here you have two examples of allocating two different blocks, and the top block and so the two blocks are fairly similar, except that the top block has a significantly lower grade than the bottom block. So you'd expect the top block to be normally sent to the to be more likely to be sent to the plant than to the bottom block. However, the neural network tends to send the top block to the plant crusher, even though it has lower grade, and to send the bottom block to the bioleach versus the cutoff grade policy, which makes the opposite decision. And to see why, you can see that in the top situation, the neural network inputs tell it that there is not much, actually, there is no material that's being sent to crusher C1, and the amounts of material that are on the feed piles at the different plants are fairly low, and definitely lower than what happens in the second scenario. So in the top scenario, it seems to make more sense to send the material to be crushed because there are no waiting times, and it can be crushed right away, and because it can ensure that the plants will still be fed something and produce something. And in the bottom situation, there is enough material on the crushers and on the feed piles to basically guaranteed sustained production for a little while. So there's no need to send this particular block to one of the plant crushers. All right, so in this presentation, I showed you how adaptive decisions in the mining complex can be made using neural networks. And like I was saying before, these neural networks are in some sense pre-optimized through this training process to make decisions automatically for new situations. So this can be very fast. Once they're trained, these decisions can be made at a rate basically takes much less than a second to make each of these decisions. So this results, together with a stochastic model of the mining complex we built, this means that less than 10 seconds is required to sample the basic cumulative cash flows that you would get for an entire year. So this is without any parallelizing and without too much optimization. And with some improvements, we believe that you can get something that is fast enough to try to begin to integrate it with strategic or long-term planning. And we saw an increase that's fairly significant over the value of the best cutoff grade policy. But I believe that this is just the beginning, and that by optimizing other components of the mining complex, you could increase the value quite a bit more. So you could look at optimizing extraction, so shovel movements, where the shovel should go next, when you have different options. You can optimize in this case we use the basically heuristic to determine what plant each crushed block should be sent to, but this can also be optimized in future work. You can optimize the allocation of the hauling fleet to different shovels. You can optimize the operational modes at the plant, and so on and so forth. So yes, the artificial intelligence methods are getting better at a very high pace, and we believe that they can be integrated within mining complexes to address all of these problems simultaneously eventually, and obtain significantly more value this way. That is all. Thank you.